I'm going to talk to you about Mayotte. So when I say I'm at the observatory, I'm actually in La Réunion, which is another island at the Observatory of Piton de la Fournaise. But I work mostly on the Mayotte seismovolcanic crisis, which I will show you on the map. So what I'm going to show is it's different collaborations with a lot of people in the scientific community, mostly France and some other people. And again, don't hesitate to ask questions. Wait, okay. So again, just to show you, I'm actually around here. Do you see my mouse? Yeah.
Yes, yes. Yeah.
Great. Okay, so Réunion is around here, but my subject is more around here, and it's been studying the Mayotte Island and what has been happening since 2018. And so Mayotte is one of the islands of the Comoros archipelago, so between Africa and Madagascar here, and it's in the archipelago. It's the island which actually looks kind of in the middle, but it's the most eastern of the real, let's say, islands, because the others are mostly sand, let's say. And so the origin of this zone is actually not really completely understood still. And there's still some debates, because for quite a while, well, I guess maybe until 2018, maybe the main idea of what the system was a hotspot. Because if you look at the elevation, you can see that the most eastern islands are the lowest, and also the last, the only active volcano was Karthala on Grand Commun. And the seismicity was quite moderate. And so there was this supposition that the zone was a hotspot. Okay. So this is kind of showing the situation in terms of what is understood. And so you have, so the system is quite complex, and this zone between Africa and Madagascar is really not like starting to get understood, but this limits around the Comoros Islands is not really defined yet. Like, for example, it is not completely clear still if the crust is oceanic or continental. So that's kind of a big thing that it's really not understood very well. And so with this new crisis in Mayotte, it's been a lot of people have been interested in understanding what was happening and in this very interesting and not really well-known zone. And so in one of the last, another theory, because with the new eruption in Mayotte and with the ages that were made on the island, it seemed that the hotspot theory doesn't really work anymore. I mean, if the oldest volcano is just starting to erupt, it's kind of contradicting the idea of a hotspot. And so the new idea now is that it would be a limit between the Somalian plates and the Luandel plates, and so that it would be, and that the system and all the volcanoes would be linked to shear deformation. And so that's about Mayotte. Now, no, sorry, that's about the archipelago. Now I'm going to focus on Mayotte. And if we look at the bathymetry in Mayotte, so that's the left side, what you can see is that Mayotte is a very big, is an old, very big volcano that has eroded for a long time, and that is now actually very flat. But it was active for quite a long while, and the last activity was 4,000 years ago. Well, before, again, when I say this, I say before 2018. And there's been a lot of activities. If you look on the right, all the black dots are cones, are volcanic cones. So there was activities even more quite recently compared to what was thought before. And then, okay. And then 2018 happened. And so in May 10th, 2018, a strong episode of seismicity started. So I was saying that the seismicity was very moderate. So the last earthquake that was felt was in 1993, I think. And so when suddenly people felt earthquakes all along the day for about a month, the inhabitants first got very scared, which is kind of understandable. And the whole scientific community and like the French authorities, and I mean, everyone was very surprised because no one was expecting something like this, and such a big seismicity crisis. And so it started in May 10th, and it has oscillated a bit, but it's still continuing today. It's still happening today. There's since a lot of things happening today. And so the French, mostly, I guess, the French scientific community, well, the scientific community in France, don't have to be French, has worked a lot on this subject to understand what was happening and how the system could evolve. And so, okay. And so with the seismicity, because with the seismicity, first, you don't really know what is happening, like maybe it's a volcano, maybe not, who knows. And then in about early June, deformation started. So the subsidence of the island started, and then there was a movement of, quite a big movement actually, of around 20 centimeters of the displacements toward the east, which kind of gave clues that this may be linked to a volcano. And then, so this is just putting at the same time the seismicity, the cumulative moment here, and the eastward moments, the eastward motion movement. And so you can see that it starts with seismicity, and then boom, it's followed by deformation. And another event another type of event, I guess, that suggested that this could be a volcano are the very long period events. And so this is the big one. This is one that was recorded in November all around the globe. And so these events are usually associated to volcanoes also. So the clues were definitely there. But then the new structure was finally observed directly, I'd say, in May 2019, so a year after, where a new volcanic edifice was found. And so in the left, you can see the bathymetry variation. So there was measurements of bathymetry in 2014, where you can see how it was before, and then the 2019 campaign, where you can see what happened after. So you can see this new structure of about 800 meters. And that happened in just a year. In just a year, you have a big structure of 800 meters that just was created. And so that's quite a big thing. It's the biggest observed, let's say, and it's the second recorded after Laki in Iceland.
Sorry, Lise, would you show us where are the GPS station seismicity distribution and this very long period seismicity in the map view?
So the stations are on the island. So so the seismic station, I guess it doesn't matter. At the beginning of the crisis, there was only one seismic station, and it was around here. And then you have GPS. You had a few. There were a few GPS stations also on the island. So so the structure is about 50 kilometers. The new edifice is about 50 kilometers from the island. So so that the fact that the island still moved 20 centimeters is quite big for such a distance. Did I answer your question?
Well, I'm just wondering, where are the earthquakes in this 5.9 event? It's at like right beneath the.
Oh, I'm going to talk. I'm going to definitely talk a lot about it after. But there are two clusters. Let's say there's one that goes around like something like here that we call distal cluster, because it's the one that's the more far from the island, and then there's a closer one that's around here, around 10 kilometers from the island, that we call the proximal cluster because it's closer from the island. But I will talk a bit more about those later. And so, yeah, something else that was observed is acoustic plumes, like very big acoustic plumes, because usually, so acoustic plumes linked to the gas emissions and things like that, that were very high, and this type of big plumes had not really been observed before. So that was also quite an impressive thing, let's say. And so now I'm going to talk about the seismicity. And so that's what I'm doing at the observatory. My work is to try to understand and monitor the seismicity in as much real time as we can. And so for this, we follow daily where the seismicity is it evolving, because we really want to see, like, because the system is quite complex. So it's always like, can the system evolve to lead to something that could put in danger the population? And so this is just an example of a monthly report that we do about Mayotte. And so here you can see the different stations, actually. So the seismic stations are in orange. That's what the network is now. And then the green ones are the GNSS stations. And then we also have some ocean bottom seismometers, geophones, offshore. And so you can see that there are those two clusters, one that's around here that gets to the volcano that is here, around here, and another one that that's the proximal cluster that is here. And so one important thing when we want to monitor the seismicity is that we want to do that automatically to have as fast as possible information about what is happening. And so part of what I've been doing is trying to develop such a method to try to, in real time, have this evolution of the seismicity. And so for this, I used the method FaceNet, which is a machine learning method that's a supervised machine learning method that was trained on data in California. So it was trained on 234,000 events with the network of Central California and North California. And so one interesting question for me was, it's trained in California, which is a very, very different system. Is it going to work on the volcanotectonic seismicity? And it turns out, yes, it actually works very well. And so we've been using this method for automatic picking of the phases of the earthquakes that arrive in Mayotte. So this is, again, just to show you the network of stations that we have. And so the volcano is here, and the stations are here. And this is just an example of an event for the different stations, seismic stations, and the P and S peaks that are automatically picked with the method. So the method works very well. And so we've been using it to reanalyze the seismicity that occurred since 2018, and to automatically detect the seismicity. Okay, and so first I can show you a kind of reanalysis that I've made on the one station that was there before. So as I was saying, there was only one station at the beginning, and so that station is here. Because since there wasn't much activity on the island, and there was no expected volcano around the island, there was only one seismometer, and so there's only one station that really followed the crisis from close, let's say, and so that's why it was interesting to reanalyze the seismicity from this data. And so we did that from 2018 to 2021 to, this should be, yeah, this is May. And so if we just zoom on it, and so you can see from the beginning, you can see here, you have, this is May 2018, where you can suddenly see the onset of seismicity. And so this has been associating with a dike, where when the magma just came up, and then it went down. And then the seismicity has been going up again, and now it's been slowly decaying. The other curve that I show is the modeled source flow rates from deformation. And so what you can see is that apart from this first episode of seismicity, the seismicity seems to follow the deformation. So the seismicity has been directly linked and the direct, let's say, kind of consequence from the deformation linked to the emptying of the reservoir.
Sorry, what is the source flow rate? What is?
So the source flow rate is it's the magma emitted. It's an estimation of the magma emitted from the deformation measurement. So from the GNSS data.
Thanks.
From the displacement that's observed. So on land. So of course it's not a perfect observation because it's far and it's only on one side. But it was possible to model this the emissions at the volcano from these measurements.
So the source is placed at the surface, right?
No, the source is also inversed, and so the source has been inversed at around 35 kilometer depth.
Okay.
But again, like it's not, of course, because the stations are only on one side, the location is not exactly perfect, of course, but it's also around where the petrology analysis have placed the reservoir. So it still is quite consistent. And so as I was saying, like one of the idea, I'm not going to talk too much about this, but one of the big things was to do real-time monitoring to really follow the seismicity because it's one of the main indicators with the formation of the activity of the volcano, of the volcanic structure, let's say. And so we developed a process to be able to use the peaks, the phase peaks from FaceNet to then identify events and locate them automatically to have really a detection in real time. And so we've been doing that. We did that. This on the left is just to show for 2 months the result that we had. What it mostly says is that we detect a lot more events than what we did before, because the method that was used before was an amplitude ratio, so STA-LTA. And the problem with this is that, well, there are a few problems with this, but one of them is that, so as I was saying, there was only one station on land before the activity, and then suddenly there was a lot of activity that was important to monitor, and so the stations were installed. The other seismic stations were installed very quickly. And because of security reasons and to do it very fast, most of them were, well, all of them actually were installed at City Hall or at schools. And so they are very noisy. And that's something that's still a problem today. We're working on installing stations in less noisy places, let's say. But it's been actually quite difficult. But if you look at the day-to-night ratio of seismicity, it's crazy. Like during the day, it's very hard to have events, to really see events. And so an amplitude ratio method cannot really detect very well the seismicity because of how noisy it is. And so that's why also FaceNet was interesting because it could still pick events, although the difference day to night is still there. And it also has the P and the S phase, which helps for location. And so yeah, and so this is just in a bigger. That's what the purple points are what the locations and detection look like before, and the blue ones are what it is now, and they correspond a lot more to the actual seismicity. And so that's now the method that we're using now in real time. So it's been running since March 2021 to detect automatically the seismicity. And so we're now also working on using this process in other places. But what I wanted to show you, to talk to you, I guess, a bit more about is the reanalysis of the seismicity. And so this is just very quickly to show you a paper that was just accepted. This is a reanalysis of the seismicity using both the land station and OBS data to analyze the seismicity. And what it showed is that we have these two clusters. I will talk about this more later, but I just wanted to show this quickly. And so we really have these two clusters that don't seem to be really connected at this time. And so, and one interesting thing that I don't know if you see it very well, but the proximal one, it really has the form of a donut. And so it's really a circle of seismicity with not really much seismicity in the middle. So that's also a very interesting system, because the east seismicity seems to be kind of, let's say, obvious, like more clear, because it followed the dike, and so it followed the magma coming up. But then there's this this west seismicity, which is not directly connected seismically, at least. It wasn't really clear before, and it has this circular shape, which means that it's more also linked to a system that was there before, because there's also a caldera around here, an old caldera. So it's a very complex and very interesting system that we've been reanalyzing to understand its mechanism. And so what I'm going to talk to you is this seismicity, and so the reanalysis with automatic detection using the FaceNet method. And also I wanted to talk to you about the different types of seismicity that there are. And so you can see that there's let's say the most common types of seismicity, so the volcanotectonic. I will show you a figure later. But this is the one, and also, by the way, you can see, so these are seismic signals for a few hours for the different stations, so the orange are the Mayotte stations, and you can see this thing that happens very regularly. So this is the air conditioning, for example, system that's next to the seismometer, and so it really shows you like how noisy this is. But yeah, so you have the volcanotectonic seismicity, and there are two other types of seismicity. What we call the very long period, which I showed you an example before, and the long period seismicity that seems to occur with the very long period seismicity. So there are different types of seismicity that show us different things and help us to understand what is happening there. And so what I've been working on has been so reanalyzing the seismicity, but also separating this volcanotectonic seismicity and this long period seismicity, or LP in short. And so if you look at the first two lines, so maybe just focus on the signals, you can see on the three components, the vertical east and north, you can see a volcanotectonic events here, where you can see very clearly the P wave, and then the S wave, and then just the S wave on the horizontal components. And then if you look at these other events that we call long period events, they can also be called hybrid. It depends on how to define long period events. It depends on which paper you read, but we call them long period events for simplicity. And so you can see that they do have a P wave and an S wave, but it's a little less clear, but it's also just longer period. And so the question was, well, I guess we got a clue seeing here that they do seem to behave differently, but we wanted to see long-term how they worked. And so I differentiated the two, after automatic detection, I differentiated the two types of events by using spectral ratio analysis from the P wave, the P phase, and the S phase. And it's really just like the longer period is going to be the LP event, the long period events, and then the shorter period are going to be the VT events. And so after this, we made some statistics. And so this analysis is from March 2019, just because that's when we had enough stations to really be confident about an automatic detection and automatic location method, because with just one station, it's just not possible. I mean, other stations from more far, like from Cartala, for example, where you could be used, but then the location is not really precise. So I just wanted to really be consistent in terms of the stations I was using. And so if you look at the first line, you can see that, so in green, you have the volcanotectonic events, and in yellow, the long period events. So what you can see is that definitely there are a lot more volcanotectonic events And then if you look at the other one, this other one shows kind of the cumulated events in time. And so what it shows you is that the volcanotectonic event, so they were more at the beginning, but then they kind of seem continuous, even though they're slowing down. But the long period events are kind of different because they happen in swarm. And so that's why you can see those steps. And they don't really seem to be slowing down. So that's another kind of interesting point. And then if we look at the locations, this is the location that we get from the automatic analysis. So from March 2019 to February 2021. So that's 50,000 events. So that's a lot. But what we can see is that this is everything. Of course, not every location is perfect. But what we can see that, for example, in the distal cluster, it's really mostly volcanotectonic events, whereas the LP events only seem to be in the proximal cluster. Then if we focus on the volcanotectonic events, so these are in the two clusters, and this figure shows you in bins of locations, the average, the median location of the events. And so what it shows you, for example, if we look at the distal cluster, which I guess is the easiest to look at, you can see that going through the volcano, the seismicity seems to go up, which is kind of expected. And then in the proximal cluster, it's actually a lot more complicated. You can see that it varies. There are some shallower seismicity to the west, and then it's deeper northeast. And so this seismicity varies a lot, and it's quite interesting to see. And we also wanted to see the evolution of the seismicity. And so, for example, so this is the work of a postdoc at IPGP. And so if we look at the distal cluster, and so with time, so this the top diagram varies in time, and it shows and the color shows the depth, and then in the vertical axis is kind of when you go up on the axis, you go towards the volcano, basically. And what it's been showing is that with time since 2019, we've seen some shallower seismicity that was also going towards the east. And that's kind of what we see in the bottom panel, which shows, in this case, each panel represents a different time. And so we can see that the shape of the seismicity has changed a little bit. So that it was lower, and then it has gone a bit east and then a bit shallower, at least during that time. Okay. And then if we look at the proximal cluster, this is just so looking at the proximal cluster and taking a north-south axis and projecting on that the seismicity. And then the color, this cluster is quite complicated because a lot of things are happening, but the color is day since 2019. And so what you can see is that the system has been evolving. Like you can see, for example, at the deeper west, no, this is deeper south actually, side of the cluster, you can see some recent activity that you can see also on this other diagram that's west-east representation. And so you can really see that here it's kind of on the right one, it's kind of clearer that the seismicity seems to extend to the outside of the cluster. So it kind of seems to show some type of evolution in the system, and maybe some fracturation that seems to get to the outside that was there around the center, and that maybe seems to be getting like more and more outside of the cluster, as if the system is kind of extending in terms of its fracturing. Yeah. And so yeah, that's a very, and then you can see a lot of other axes that show you a lot of things, but a lot of things are happening around here. And so this cluster is still very active. And I think there was something else I wanted to say, but I forget. And then if we look in this case, we're still in the proximal cluster, but here we're looking at the long period seismicity. So as I was saying, the long period seems to happen more in clusters. And so the top panel is a representation with depth, and this is Julian day. So this is from March 2019 to February 2021, and these are just all of the events. And what I wanted to do is to see if there was a behavior in a cluster, in a swarm, like are the events behaving a certain way, or is it completely random? Are they all at the same place? Are they moving, and things like that? And so to do this, I selected the swarms where there was enough events to kind of be able to make a statistic. And so these are the second line. You can see like the time is the same, but this is just selecting the main, let's say, the main swarm, so the swarm that had the most events. And then the bottom figure is still the y-axis is still the depth, and so in the x-axis is kind of the number of the swarm. So this is just all of them, and just put with a number. And so then I tried to see if we could see a consistency between their behavior. And what you can see here is that, for example, I don't know, if we look at this one, 12, very randomly, what you can see that inside of a cluster, and I used a regression function to see the consistency and see the behavior of the events, is that the events seem to go down, which wasn't naturally what I was expecting, because long periods are associated usually with fluid movements or with a resonance of some kind. But I guess in my mind, it was more fluid. And so when I think fluid, I just think up. But in that case, it seemed that quite consistently, in a swarm, the event seem to go deeper. And so that's been quite interesting. And so the numbers are the velocity of them. And so what they say that usually we have a cluster that will last for about half an hour or something. And then the event will go from 20 kilometer depth to 45 kilometer depth. And so it's really, and they all seem to be around the same place. So center east from the proximal cluster. And so they all seem to kind of do this going down thing. So which I expect, my idea is that it's more linked to a kind of resonance, also because they still look quite close to volcanotectonic event, but just with longer period. And so these events are also linked to the very long period events, which seem to be a bit more shallow, between 10 to 20 kilometer, and that's the work of a PhD student, Angèle Laurent at IPGP. And so just to summarize this, so this is just a summary, like what happened and things like that. So seismic crisis, displacement, and then the eruption was observed. And then there's all these types of seismicity, which you can see at different locations. You have the VT seismicity in the distal cluster that seems to kind of maybe follow the dike. Then we have the volcanotectonic and long period seismicity, but they behave a bit differently. The volcanotectonic seismicity seems to be really fracturing, that's evolving with time, and the long period seismicity kind of seems to be behaving always kind of similarly, like going down, going at depth each time. And it happened at the same time of the very long period event, which seem to be a bit shallower. So that's also an interesting, complex thing that we're trying to explain. But the seismicity really seems to show quite a few things about that. Do I have, how much time do I still have?
It's up to you. So we usually try and finish it about 1:45 or 1:50, but whenever.
Okay, so I will just show you something very quickly, just because I wanted to show you another type of signal that we've been looking at, but I'll go very fast. So we've seen the deep, kind of the deeper seismicity, but now there are other signals that we were able to observe on the OBS data, which are the hydroacoustic signals. And these hydroacoustic signals this is a representation of the lava, of the magma, of the eruption. And so these signals are linked to propagation in the water layer. And they are also recorded on the OBS data, and they really show us a very different view from the seismicity at depth. They show us really what is happening around the eruption, and so they're very short signal that really bounce in the water layer, and that we can analyze, and they help to follow the eruption. And so these are just a few examples of these events on an OBS station that was close to the eruption. And there are a few different types, but usually they're very impulsive signal, and that propagate in the water layer. And so you can see for example, for this station here, you can see the first arrival and then another one, and then here we don't really see a third one, but then the other station also show this behavior. And I just wanted to show you also the location. And so for the first year, all the eruption was around the new volcano, the new edifice. And then after, to the one that's been actually more studied, because that's when we could have oceanic campaigns and to really go on site and make bathymetry measurements. These signals, these hydroacoustic signals, have been coming around from here, which are the late eruption sites. And so we've been using this signal because a campaign can be only every few months. We can't be every day there to see what the seismicity variation is and how everything is evolving. And so this signal can help can help really at the eruption to see how is it evolving. Is it continuously? Does the lava seem to be evolving continuously, or are there steps? And so this figure kind of shows this. This is just a 10-day period of the time difference of arrival between the closest station and the other two close station, and it just really shows a variation of the location, because the y-axis is the time difference between the first arrival on that closest station and the two other stations. And so what they show is that you can see some evolution in this time, so which show an evolution in terms of the location that we can kind of follow during the period. And it kind of seems to happen in steps, which is interesting. It's not really a continuous following of an eruption. Like, it doesn't like just go as smoothly, but it goes in steps. And then what we can see also is that at the end of that period, suddenly the events seem to slow down. So this was really just to show very quickly, like, all the different types of signals that we can observe with seismology, and what they can show us at the different depth of or surface of a magmatic system. And I guess that's what I wanted to show. So thank you.